For the next couple of sections, we're going to be looking at what are called parametric equations. So most of your life, you've been doing what we would call Cartesian equations. These are equations that relate x and y to each other with an equal sign somehow. So that's Cartesian. A parametric, instead of trying to relate the two variables directly to each other, we are going to relate them independently to some parameter, hence the name parametric. In this case, I've written it as t. T is our parameter the way I've written it, but it doesn't have to be t. Typically, we use the letter t because typically that parameter is time. One of the main reasons we want to start looking at parametric equations is that if you're going to describe motion, if you only have x and y in 2D space, you can describe the path. So, a Cartesian equation would have no problem describing a path. But the problem is, it's not going to tell you anything about the motion along that path, right? So you might have had a curve like this in Cartesian, but all it tells you is this is the location the object will be along. But when is it here? When is it there? How fast is it going? Is it speeding up? Is it slowing down? None of that can be described because motion is a function of time. So we need to introduce a time element, and that's what this does. Each time, so you might plug in t equals 0 and get some xy pair. So you might have a location right here when t is 0 that tells you that you're right here at time 0. Then you could plug in t equal 1, for example, if we're just going to go by increments of 1 second or 1 hour, whatever t stands for. Maybe when we plug in t equal 1, we get this point. And when we plug in t equal 2, we generate an x and a y that puts us right here. And so now what we'll get with all of our t values is not only the path of the object, but we know exactly when the object is at each location along the path, which then will allow us to do things like calculate velocity and acceleration and such. Now you might think to yourself, well, hold on a second. In Calc 1, we did velocity and acceleration. Now you're telling me we couldn't have. Well, think about what you did in Calc 1. You had objects moving only horizontally or only vertically. So really, you were, in essence, we didn't use the term back then, most likely, but you looked at just that for horizontal motion. You had x as a function of t. So really, you were looking at a parametric equation, a 1D parametric equation. Or for throwing an object straight up and having it fall back down, you might have looked at just y as a function of t. So you were really doing parametrics already. So now what we're doing is combining those together to get a 2D picture. And that's really as far as we'll go, but this easily generalizes. And when you move into multivariable calculus, you're going to want to describe real, true, three-dimensional space. So then you can just add a third equation. So in 3D, which we're not going to really look at, but you'll look at in Calc 3 for sure, all you have to do is tack on a third equation for the z component. Z coordinate, I should say. So 2D or 3D. And so what this is going to allow us to do is describe motion. That's probably the biggest reason we want to look at it. Now, in Calc 3, there's another benefit. It turns out that when you're in three-dimensional space, you have no options. This has to be the way to do it. A Cartesian equation, if you try and write an equation that relates x, y, and z, say x plus y plus z equals 4, you're going to get a plane. Equations involving x, y, and z will generate surfaces. So actually, even if you don't care about motion, the only way to get a curve in three-dimensional space is with a parametric. So parametrics become crucial once we move to 3D. And we'll be talking about curves in three-dimensional space in Calc 3. So t for time, but parameters could be other things. Another common one is to use an angle. As things rotate around, the parameter might be theta, our unit circle theta, describing locations as you rotate around. So there could be other parameters, but the most common one is time, because we're most often interested in motion. So that's what we'll be looking at. And so what we'd like to do with these parametrics is first just kind of look at some common shapes, circles, lines, and see how we can write parametric equations for them. And then we'll do a little bit of calculus with them. Can we calculate the slope on something like this if it's defined this way? Or can we find area under the curve and those sorts of things? So we'll do some calculus with parametrics as well. So that's what we'll be looking at for the next couple of sections.